hedgehogs and things you play on video games.
Teach it to retrieve. Teach it to retrieve. Does that to be?
Is a cat real bad?
Someone retrieve.
Dude, they all retrieve. What are you talking about? You throw a house, they'll go bring it and drop it at your feet.
Yeah, that's fair.
Taught my cat to sit, heal, everything.
My cat's
Okay. So the plan for rest of the semester, we don't have more holidays, unfortunately. So there's about 6 meetings in class and 2 meetings in the lab, right? So the plan is as follows. There will be 3 meetings with primarily academic material and 3 meetings related to projects. So on the coming Wednesday night, we all will complete basically everything for the projects. Maybe with leaving a little loose ends. On coming Friday, I'm asking you to bring in class written reports. So whatever you complete on Wednesday, type it in Word as you do for like labs. I'll tell more during Wednesday what to type in. And print 3 copies and bring on Friday. Okay?
3 copies?
3 copies. You can imagine why. Right? And then on the next week, on Wednesday, you will all complete movies based on your projects. And by next Thursday night, submit PowerPoints, and last Friday of last meeting, there will be presentations. Good? Oh. So, 1, 2, 3, 4, 5, 6. Well, probably our last meeting will be number 42, and instead of these materials, it will be just final presentations. So, here is where we are. It's more like notes for myself. If you didn't get enough support and help, approach me, send emails. I'll twist arms of graduate student helpers, so to progress forward. This, I'm just showing general lines how to do it, but it is for those who do chemical projects, where one tries to change temperature and see how the reaction goes over activation. If it is better, if it is something different, we'll modify different parameters. So what we did last time, there was a trick. I'll give you a wake up sign when you need to concentrate or write down. Keep relaxing. So last time we were focusing on rotation, which is either electron around nuclei, or it could be diatomic motion, right, for rotational spectrum. And it is a natural wish of physical chemists to set up Hamiltonian and then to diagonalize it, find eigenvalues and eigenstates. But diagonalizing Hamiltonian for rotation is not as pleasant, so we used the commutation principles. Like if the Hamiltonian and another operator do commute, then they share the same set of eigenstates. Therefore, instead of diagonalizing Hamiltonian, we were diagonalizing angular momentum operator for 2-dimensional rotations, right? Which is attractively simple. And so operator, eigenvalue, unknown function. And then we used this functional form with 2 unknowns, normalization coefficient and quantum number. And when we found them through some Euler and trigonometric tricks, we found the solution, right? So it is same as plane waves, or same as particle in the box, with the difference that p-varying boundary conditions are different. And there are only specific values of this eigen quantum numbers. if you look for energy, we just plug in these eigenstates into the prescription to find expectation value of Hamiltonian, and those will be the energies. I is inertia, m mass times distance squared. And what is interesting, there is a degeneracy. So every number except 0 has two states with the same energy. If you go from two-dimensional rotations to three-dimensional rotations, we were not and we will not solve for it. But if you do it, there will be the degeneracy for each energy associated with rotational energy will grow. Like 1, 3 degenerate, 5 degenerate, 9 degenerate. And instead of quantum number squared, it will be quantum number by quantum number plus 1. This is what you will see. Keep collecting. I'll let you know when to look up. It is important for rotational vibration spectrum. By the way, this 1 over inertia is a rotational constant which can be found experimentally for any diatomic. And if you would have year-long courses, it will be like set of homeworks. Like what is the rotational constant for H bromine or like different gases. So, summarizing, if we do want to do spectra, rotational spectra, we do need initial state, final state, oscillator strengths, which we do not know how to find, and right now it is not so important. And also, there will be multiplied by, if some energy levels are degenerate, there will be also degeneracy plugged into here. Degeneracy. So if we need a spectrum, we need like quantum numbers just to count states. We need degeneracy, which relates to number of states in our description of particle in the box. 1, 3, 5, 7, 9. Then energy levels. Because of this equation L times L plus 1, the N times rotational constant, the energies progresses as 0, 2, 6, 12. If one starts from the lowest. And the, remove D here, it was wrong. I was doing it in the middle of the night, not very same. So, then transitions, there will be also selection rules imposed into this oscillator strength that transitions are possible to change rotational quantum number only by 1. Therefore, one needs offsets between nearest neighbors. And the offsets are 2, 4, 6. So here are these offsets. And one can just subtract this L times L plus 1 and get these offsets. So if this information is plugged into set of levels, vibrational level for ground state and first vibrational excited states, one needs to take into account another factor, that Boltzmann distribution. Those levels that have smaller energies are more populated, those that have higher energies are less populated. And if one takes this ratio of like vibrationally excited to vibrationally ground, Boltzmann distribution, and merges it together with degeneracy, one will have two opposing trends. One trend, if we take into account transitions with higher energy, intensity should grow because every higher state is more degenerate, has larger degeneracy number. But on the opposite, there is an opposite trend. As higher the final state is, as higher the initial state is, the lower is the population. There is a Boltzmann factor. And when these two factors, one growing and one decreasing, meet each other, one is getting these two wings. Here. So So because degeneracy grows, and then because the Boltzmann distribution falls. So this is main principle of vibrational spectroscopy. So position of this peak depends on temperature. At higher temperature, it will move away from center. At lower temperature, it will move closer. This offset corresponds to inertia. Whew. Keep relaxing. So if today's meeting will go successfully, we will end at this slide, or maybe a little bit further away. This is very boring, and I hope I will be repeating it. So it's not top important, but if you are in doubt to relax or to concentrate, it's like moderate level of importance. So you may consider to focus. There is no doubts in your math background, intuition in physical chemistry and skills. There is just lack of time. So I will offer some oversimplified material, not as disrespect to your abilities or mine abilities, just to fit some information in time. You all know that electrons are quantized, right? So they have quantum features of motion. And in the first, I don't know if it's most important, but first application of quantum theory to real world hydrogen atom, one needs to quantize electron motion in all three directions, x, y, and z. Or if you introduce spherical coordinates for rotation and for motion inside and outside. Electron coming to nuclei, approaching nuclei, or departing from nuclei. This is like one of the cornerstone of human civilization, but it would take another 2 or 3 weeks to do it in details. So I will squeeze everything in today's remaining half an hour with substantial simplification, which is not 100% correct. But since 1913 to 1927, it was accepted as ultimate truth in the community. So it will be Bohr's model for hydrogen atom. We all should understand that it is a simplification. So for your level of knowledge in physical chemistry and math background, it will be like kindergarten. The plus of Bohr theory is that it reproduces experimental spectra for absorption and emission of light. The energies, not the intensities of lines, but actual at which energies the peaks will be observed. Everything else is disadvantages, minuses, but this was a really strong leap through in human civilization. So there will be not much math, but at the time Bohr's theory was developed, there was no Schrödinger equation. So instead of solving complicated mathematical equations, it was more like philosophical, intellectual effort. And we can try to follow it with understanding that if we look, and Bohr's model is not fully quantum, it is half quantum, half classical. Specifically, rotational motion in Bohr's model is quantum, and approach or departure of electron towards the nuclei or away from nuclei is classical. This is like big simplification, but it will give right answer. So if we will arrive to the slide, so what is shown? So the outcomes of the Bohr theory is that there are three things that take discrete values. Angular momentum, that is not a big surprise after previous two lectures. Distance between electron and nuclei, and energy of electron. Three things are quantized. And based on our previous practice with quantized two-dimensional rigid rotor, we can accept the idea of quantized angular momentum. But in our previous consideration, we didn't have any restriction to the distance between these two rotating objects, between like electron and nuclei. And we didn't, and the energies were taken discrete but very dense spectrum, as we covered over in this rotational spectrum, right? So you have quantum number and then the quantum number squared. So many, many levels. So in rigid rotor, we didn't have any restrictions to distance. It was just set up for given rotor the length. And we didn't have too many restrictions on energies. If we consider hydrogen atom where electron not only circulates on the orbit, but can approach closer or depart further, there will be additional restrictions. Okay? So the main, now probably try to wake up. I'll try to verbalize main outcome. The main novelty, main idea of Bohr's model and what we will cover today in the lecture, that forces between electron and proton do depend on angular momentum, on the amount of rotational motion. So when the electron rotates quicker or slower, it is attracted to nuclei differently. It may sound trivial, but try to, if you count on your memory, memorize, or maybe make some marks in your notebooks. So forces between electron and nuclei depend on amount of rotational motion. And this is not a new idea for classical mechanics, or you know that satellites sometimes fall down and get burnt in the atmosphere, right? Because when it moves slower and slower, it has friction with the atmosphere, and it attracts less, and it starts falling. Right? When you accelerate it a lot, it will go on the higher orbit and more stable. But difference between satellite and hydrogen atom is that satellite can take any distance and any amount of angular momentum, and electron and hydrogen atom can have only discrete values of angular momentum. So these lines, dashed lines that we will get by the end of the meeting, are the energies of interaction between proton and electron for different value of angular momentum. So if the angular momentum is minimal, according to Bohr's theory, it will have deeper potential with minimum at one atomic unit, and energy minus half atomic units. If the angular momentum is higher, is 2 Planck constants, it is less deeper and it will have minimum at 4. If it rotates even quicker with different angular momentum, the minimum will be so at 9, and it will be even very shallow. So this progression of energies, -1/2, -1/8, -1/19, and there is a progression further. Those, it agrees with experimental values of energies of hydrogen atom, and transitions between them will reproduce spectrum. So if you get this idea, you are done for today. I will try to give a little bit more meat to these bones and try to reproduce logic of Niels Bohr, where it came from. I'm already tired. We should submit a petition that lectures will be 20 minutes, not 50. Okay. So middle school physics or high school physics. If you have a rope and something heavy, you rotate it, right? And then you release it. If you keep moving. Same like biblical story of David and Goliath. Right? But if the rope is, you do not release the rope yet, right? And something moves on circle, you can mathematically put the vector that will point on your mass, and then velocity will be always tangential. What is interesting, so you didn't catch me, because I didn't tell something wrong, but it is important. The angle between vector from center to rotating stuff and velocity is always pi/2, or 90 degrees. Right? So if we, just because it is tangential. Now, if we move for a shorter time or a little angle, and we draw this velocity vector at each point, we can consider vector difference, vector subtraction of the velocity at different time steps. Infinitesimal change of velocity. What is the infinitesimal change of velocity, dV? What does it correspond to? How do you call derivative of velocity over time?
Sorry.
Derivative of velocity over time. When you pedal to the metal, what do you do? What your car does?
Position.
Not integral, derivative. Yes, it's acceleration.
That's what I said initially.
Yeah.
Okay.
Okay, acceleration. So this, if you put, you translate this vector and just connect these two arrows. So it will be this dV, right? Which is acceleration. So what can you observe on this little cartoon? Geometry at the level of like kindergarten or like middle school. Nothing too scientific, nothing too mathematical, just orientation in space. So the green arrow is perpendicular to red arrow, right? The black arrow is perpendicular to green arrow. What is the relation between black and red? What is the relation between acceleration and position vector?
Opposite.
Opposite, yes. They are collinear and opposite. So how do you interpret it? Let's interpret it verbally. So if an object is moving on circular trajectory, it's not natural. It means that someone applies force, acceleration towards center. Right? So circular motion witnesses of the acceleration or in the direction toward the center. So there should be some force. if something is moving on a circle, it is an evidence that there is a force that pulls it toward the center. Good. You all know angular velocity. Like if you divide length of this trajectory over velocity, it will be period. Or if you divide velocity over length of this circular trajectory, it will be frequency, right? And if you multiply left and right by 2 pi, it will be omega, angular velocity. So, one of your best friends is Euler, which means you are masters of circular motion. Maybe you didn't recognize it, but you do. You are. So if something is moving on a circle, it means a two-dimensional circle. The projections, like if radius vector moves on a circle, it means that projection on x changes in time as cosine, and projection in y changes as sine. Or if you want to merge it together, we can put it as initial vector, which can be oriented along the x-axis, times imaginary exponential with angular frequency in the power of this exponential. Just by, so it will be real and imaginary components for x and y projections. Right? It doesn't surprise you. Now, just repeating the stuff that we did before. Okay, I don't have energy to write it down. I hope you forgive me and believe me that it is correct. So if we take derivative of this expression over time, what are we going to get? So the initial vector at time 0 will not change, but derivative of exponential will remain exponential. Okay, I'll write a little. E minus I omega t, and I omega will go to up front. Right? What if you, so it will be velocity, right? So the imaginary unit here, I, is equal to E I pi over 2. It means that there will be phase shift. Phase shift by pi over 2, which means rotation by pi over 2. So the velocity vector will be pi over 2 angle from the radius, which means they are orthogonal. So imaginary unit is rotation by 90 degrees. And when we practice derivative of velocity over time, what are we going to get?
Acceleration.
Yes, but mathematical. We'll keep this R naught. We'll keep I omega from the first derivative, and once again another I omega from the second derivative, and then once again e to the minus plus I omega t. Now each imaginary unit is e to the power I pi over 2. If we perform this operation twice, it will be e I pi over 2 times e I pi over 2 e I pi, which is equals what?
-1.
Oh, yes, -1. So we mathematically prove, not as hand-waving arguments, that acceleration will be parallel to distance vector, but oriented to the negative side. I times I negative 1, and there is a omega square because of this derivative. So acceleration is negative in respect to position. And if we believe Sir Isaac Newton, then force is mass times acceleration. Right? So we just multiply by mass. So if an object moves on a circular trajectory, it witnesses that there is a force toward the center. So does anyone speak Latin? Does anyone took any Latin? Okay, so how to, well, I should ask it before showing this slide. What will be the Latin for to seek?
Well, Terry.
Yeah, it is written here. So, and center is the same way. So if you combine these two words, like there is a force that seeks the center, right? Centripetal force. Okay. You know, right now, any scientific communications are written in English. At the time of Newton, everything was written in Latin, even if your native is English. So centripetal force, centripetal acceleration, centripetal force. Good. Now, did you ever try to rotate some mass on a rope? Or did you ever practice the sharp turns on a high speed in the car? What do you feel?
Force to the outside.
Yes. So which force moves you, like applies to you outside?
Inertia.
Yes, inertia. That's right. That's right. So you know, there are conservation laws. Energy is conserved, momentum is conserved, and there is another thing that is conserved. Rotation, angular momentum is also conserved. So if it is a simple two-dimensional rotation with these two vectors orthogonal, then distance, mass, velocity, angular momentum constant. Velocity is angular momentum divided by mass and distance. And kinetic energy, we already covered it in the Hamiltonian for rotating. So angular momentum squared over 2 inertia, mass times distance. Right? No surprise. I was not cheating. That's correct. Now, let's look on this very simple formula from different angle. Let's consider that angular momentum is a constant because nothing changes it, because there is a conservation law for angular momentum. But what can be changed in this expression for kinetic energy? If this is constant, mass is constant, number 2 is constant, power 2 is constant, distance. So it is kinetic energy, but we can consider it in the same way as we typically consider potential energy, as function of distance. Not velocity, but distance. So kinetic energy as function of distance. So we put this factor outside, it's constant, and then kinetic energy as function of distance is 1 over r squared. Right? What does it mean? How can we analyze it? So it is always positive, right? 1 over r squared will be always positive. What will be the this kinetic energy if you are steering too sharp, if the radius is really small, tends to 0? 1 over 0 will be infinity. So if you try to make very sharp turn, you'll experience infinitely strong force on you. Therefore, some people a little push the brake before the turn.
Something.
And when the distance is infinitely large, then this energy is zero. So always positive, infinite at zero distance, decreases with distance. And if you take derivative of energy is force, right? Minus derivative of energy is force. So the force will be directed where? Towards the center or outwards? When you do sharp turn with a car, what do you feel? Toward the center or away from the center?
Away from the center.
Away from the center. Anyone practiced centrifuge in the wet lab to separate? So you have little test tubes, you arrange them, and then it rotates quicker than one can imagine, like whatever, 20,000 rotations per minute, or and then you do the separation of sediments. Right? Centrifuge, centrifugal force. So centrifugal force originates from inertia, and it is directed away from the center. But before we agreed that if something moves on a circle, it means that there is a force directed in the opposite direction, toward the center. Okay? Centripetal. So if we are speaking about hydrogen atom, electron and proton, what holds them together? What will be the source of the centripetal force? Well, I'm not asking it at the right time because it is already shown here, right? What's the name of the designer of this equation?
No.
Say, I do not know how to write it differently than the person who discovered America. It's like one letter difference, but I always miss this letter.
Well, Coulomb's.
Yeah, so Coulomb's law, electrostatic interaction. So if the charges are the same, it repels. If they are opposite, one positive, one negative, they attract. And it is linearly, it's proportional to inverse of the distance between charges. So for hydrogen atom, proton +1, electron -1 attract. And in atomic units, all the constants become 1. So it is just -1 over r. Make sense? Centripetal, centrifugal. Two forces. And if it doesn't go away from the orbit, it means they compensate each other. They're equal. I hate units, but we need to accept them. One needs to take care. So for those who hate units, scientists designed nature atomic units, in which mass of electron is 1, charge of electron is 1, Planck constant is 1, and the Coulombic factor is also 1 over p for pi dielectric permittivity of vacuum is 1. So it's intentionally made to please you guys in this class, so that centripetal force will be just -1 over r. Otherwise, one would need to put a lot of constants and practice conversion. Whew. So, if you have kinetic energy and potential energy, typically one puts them together for total energy, which we sometimes colloquially call Hamiltonian, right? Kinetic plus potential. And we plug in these expressions. This is constant if we fix value of angular momentum. So one is repulsive, centrifugal, away. Well, right now it's energy, and another is attractive, centripetal. We're almost done. We're like, well, maybe exaggeration, but we went over main thing. Let's just analyze this equation. So, if you are in doubts whether to relax and sleep or wake up, it's time to, again, it's not primary urgency, but you may fall. I believe that what I'm going to say is of some importance. So, if we would play fair game with all hard bells and whistles, we would formulate Hamiltonian for electron in central field of proton, which will have potential energy same as before, but kinetic energy will be expressed as, you know, gradient over x, y, and z, but x, y, and z are not very, they're impossible for centrally symmetric force. So one would express this part as like one long line of derivatives in spherical coordinates. So derivatives over angle phi, angle theta, and distance with some factors. It's doable. You're already prepared enough, but we don't have time for it. So in quantum approach, this would be set of complicated differential operators. And then there are tricks to solve it. It's doable, but we are skipping it in this year and maybe in physical chemistry anytime. Bohr was not aware of Schrödinger equation, because Schrödinger equation didn't exist at this time. Bohr was not aware of quantum mechanics, because he was just about to design it. So, therefore, instead of really, I could put this equation to impress your imagination, but it's big. And solution is even more impressive. But one can put here angular momentum just as a constant. If you assume that it takes discrete values and we just plug it in. And discrete values of angular momentum would be the only quantum feature of this equation. In anything else, it will be classical mechanics. So we would consider potential that have attractive and repulsive part, but depending on amount of angular motion, the repulsive part will be stronger. The quicker it rotates, the larger the angular momentum, the stronger proton and electron are repelled from each other. Make sense? So, how can we interpret it? If kinetic energy, if this first term, repulsive term, is bigger than attractive, stabilizing term, then our hydrogen atom would decompose into plasma. So it will be not a stable atom anymore. It will be freely moving electron and proton. So in order for hydrogen molecule to exist, and here H is Hamiltonian, it's not hydrogen. In order for hydrogen molecule to exist, the attractive part of energy should be bigger than the repulsive part of energy. And you can see right away that for very large amount of angular motion, it is not possible. If you spin it to rotate highly, it will be just unstable, it will decompose. Also, we do not have freedom. The thing from Bohr's theory is that values of this angular momentum are discrete. And for each value of angular momentum, it will be like potential curve where repulsive and attractive parts are added together. You have already seen this figure. right? You can recall what we were looking at the beginning of the meeting. I'll show it again at the end, but how do we find radius of the orbit? Just based on this equation. How do we find where centripetal and centrifugal are equal to each other?
You set h to 0 and you add 1/r to the other side.
Well, the derivative, the gradient of energy is force. And we add together these two energies, then gradient of energy, if it is 0, it means that forces originating from these two components will be equal, right? So we just need to find where this combined potential will have minimum, right? Minimum of a function is at a place where derivative is equals 0. Okay, so taking derivative over position of this equation. So derivative of 1/r will be minus 1/r squared. Derivative of 1/r squared.
Negative 2/r cubed.
Yeah, thank you. So we can practice and add it together. So here is your r cubed squared. So minus times minus plus. Here's minus. And then we need to solve it for distance, because everything else is already provided. So we can cancel r squared, and then you leave only r here. And we can migrate, put them on the different sides of equal sign. And then we can put r here. So the radius will be angular momentum square over mass. So the higher value of angular momentum, the quicker the rotation, the longer the radius of orbit. And it goes not linear, it goes quadratical. So if we make it rotate two times quicker, the distance becomes 4 times more elongated. Make sense? Whew. And if we are enjoying atomic units, distance just angular momentum if you put Planck constant to 1. So r equals quantum number squared. Centripetal equals centrifugal. So in atomic units, enabled, allowed distances will be 1, 4, 9, 16. And distance units, the one unit length in atomic units is about half angstrom. Bohr radius. So it was derived exactly this way. So the minimal distance from electron to proton is unit length in atomic system of units. Make sense? Whew. Okay. I will take a couple of minutes from your time, but we are close to completion. So, centripetal is negative Coulombic. The centrifugal is repulsive. And depending on the amount of angular momentum, it will be higher and higher, stronger and stronger, right? When we need to find overall potential, we add together this black and this red and give this red. So at some point, the attraction and repulsion compensate each other, and there will be minimum at 1. If we have stronger repulsion, it will be this curve, with minimum at about 4. If it rotates even quicker, the minimum will be at 9. So, main conclusion. Where will be energies of this minimum? This is main answer of the Bohr theory. So we need to plug in this value of discrete radius into our total energy. We replace R by L squared. So L to the fourth, L to the second. Cancel this here. Put 1 over L squared outside of the bracket. 1/2 minus 1 will be equal to minus 1/2, right? 1/2, 1 over L squared. And it will be depending on quantum number. If we are coming into atomic units, we do not have Planck constant equals 1, and we have minus 1/2, 1 over m squared. And if we plug in 1, 2, 3, it will be 1/2, 1/8, 1/18. So it will be positions of this minimum in there. Okay, it's the last slide. Well, it is not last slide in this PowerPoint, but it's end of the meeting. Thank you for your questions. Meeting is dismissed. Looking forward to see you on Wednesday. Any emails are encouraged.
So what do you say if we redo it?
So he's gonna send out an email.
Oh, I see, okay. So,
He'll send out an email with stuff about it, and then we're gonna do other problems or something.
we're gonna do what?
Other problems that are similar to what we didn't do right. So like,
That'll be good. Did he say anything about curving at all?
so from talking to a graduate student, they said that he curves the class so that like
Kevin?
the highest people get A's. And then just
Do you have my stuff on your laptop? Were you able to do something?
No, I've just been
What'd you
going
do on
through
the floor?
the lab.
Just
I
let me
think
know
like a
how
70s.
confident you are in the project.
Okay, I'll let you know after
Got a
today. Lynn and I,
CHEM364, and I'm like,
IRB
yeah, I knew that one was gonna happen, so I thought I'd
So-
do it.
It was 7, 6.